Awesome. Thank you, Marisa. I appreciate the folks at NACWA and Kando for having me today to speak about how we use their technology and where I see some of the real benefits to both clean water utilities and public health authorities. So go ahead and switch slides there. Let's see if my animation works here, but this is a GIF specifically from the 1987 classic Predator, where Carl Weathers and Arnold Schwarzenegger perfectly encapsulate the relationship that clean water agencies and public health authorities should develop. Next slide, please. So that representation, sorry, go back one. I got a little bit more of a spiel here. This usually goes better when you can see that first animation. But this meme came up, obviously, I think it was last year it popped up, and I've used this in a couple of talks. But that handshake right there between Carl Weathers and Arnold Schwarzenegger, whether you call it wastewater surveillance, wastewater-based epidemiology, or wastewater monitoring, whatever you want to call it, the partnerships that we developed here and other places that have done this are really what is needed to maintain and grow this young and exciting field. So go ahead and switch it up, and I'll talk a little bit more about the subsewer shed study. All right, so specifically, Maurice spoke about the subsewer shed study that we talked about. Actually, we're in the middle of it right now from a public health perspective, but I'd like to talk about some of the dual benefits of carrying out subsewer shed monitoring. So not only do you gain public health insight into what's happening disease-wise at a neighborhood level, you also begin to understand what's going on within your sewers from a water quality perspective. And everybody from NACWA that's on this understands that crazy stuff happens in sewers, right? There's all kinds of weird chemical reactions that happen in it, depending on what your industrial users are dumping in or somebody from their garage dumps in, right? But I really do believe that this area is where the rubber meets the road for dual benefits for clean water utilities and public health agencies. So as a part of this study, not only were we sampling for public health targets of concern, we were also sampling 4 specific water quality parameters, which Angel talked a little bit about. But those are electrical conductivity, oxidative reductive potential, temperature, and pH, all indicators of that sewer pollution that he talked about. And this sewer pollution monitoring can be really valuable to sewer districts that are worried about the structural integrity of their sewer, whether they have aging assets or folks like El Paso, industrial users that maybe are causing pass-through interference at their plants. So now I'm going to zoom in on the area highlighted in red, where we have a number of known industrial users that we're still chasing down, and whose story I will tell you next. So go ahead and switch to the next slide. Unfortunately, my animations won't work here, but we've zoomed in on this area that we were surveilling as a part of the public health project, but we also had a water quality sensor sitting down there too. Down there in the left-hand corner is our pre-treatment manager, Andy Brome. Shout out to Andy. That's the unit that Angel was trying to show you, if you can see it down there in the corner. But one of the really interesting things that we saw during this was, and I suspected there was a lot going on, and that's why I asked them to install a water quality sensor, even though we were only looking for public health markers. But we found this pattern that we were seeing of extreme pollution events that were driven by pH. And if you know anything about what acidity can do to a concrete sewer or a brick sewer, it's going to cause problems structurally. So if you would go ahead and switch to the next slide again. So what we did once we started seeing that pattern is we took Kando's units and we placed them strategically throughout this sewer shed. And not only do you gain the, should I say, we started upstream from that area and started sampling manhole by manhole, essentially, to eliminate certain industrial users and areas of industrial users as we moved them further up the sewer shed. And we drilled up to a really far area up into the upper reaches of the sewer shed of an actual known industrial user whose wastewater stream and discharge we thought was going a different place. But if you switch to the next slide, I started examining some of the in-pipe inspection footage from that area, and I found something that was very interesting. This industrial user is a dye manufacturer, right? So you see this sort of Mardi Gras colored discharge that we were seeing here, and just downstream of it, not nice, actually, it's bad for our sewer, but the bottom of that sewer, this 48-inch sewer, had been corroded out by this discharge that we found essentially by monitoring for public health markers. We found this. So this is one of the great, I think, success stories, and we don't know exactly who it is yet. We haven't drilled it down to the lateral. I suspect that this is it, but like Angel said, we're going to take this information and then be able to present to the industrial user and say, hey, we believe you guys are doing this. You may have screwed up our sewer, by the way. So we need to do something about that. All right, so that's one of the great use cases, and I kind of flew through it, but I wanted to get through a couple last points to make sure I'm respectful of folks' time, even though I think we're getting towards the end. Go ahead, next slide. So what did we get out of it? We identified an unknown industrial discharge. What did the health department get out of it? They got really great community level understanding of public health markers, right? But really, you know, for someone like me that cares about keeping sewer collapses from happening, or keeping sewers from getting rutted out, or keeping the pollution out of our CSOs, combined sewer overflows that would happen if you are in a place that has too much water like us. Angel doesn't have that problem. Those are kind of the things that I care about. So if you'll go to the next slide. What else have we done with this? We have monitored industrial users with known violations, bad actors, if you will, that already had restricted permits that were supposed to tell us when they were discharging. We put it downstream of them and found out that they weren't telling us. So what do we do? You know, that among other things, we not revoked a permit. Actually, we just chose not to renew a permit. And we actually have a sensor on them right now monitoring their discharge, and they've been behaving. So we are able to know that. Next slide, please, just so I make sure that I get these ideas in here. Future applications, I think we're trying to find ways, or we talked a lot about it, of how we use these different data that are different places at utilities. And we've been talking with our collections group who maintains our system risk models that are out there. And we're trying to figure out a way to use this real-time water quality information to inform those. We're also exploring kind of taking it to the next step beyond the infrastructure protection portion and doing more plant protective mechanisms, though we don't have the issues with interference and pass-through. We still want to be able to give our plants early warnings of potential things that might come through, you know, whether you have big organic loads or big nutrient loads that are coming through where you might have to change your operations in some way. And another area where I really would like to dig in and have more understanding of, and maybe this tool is the way to do it, is understanding how we can characterize our combined sewer overflows from a water quality perspective. So here, historically, we've always cared more about volume, just in general, reducing the amount of volume that comes out of our combined sewer when it rains. But we've gotten really good at controlling water in our collection system. We have one of the most advanced smart sewer systems in the world. We're incredibly sensorized when it comes to flow. And I really believe that the next step is, you know, taking that to the next level and start informing that planning and water storage mechanisms that are out there that we have by water quality, taking it along with flow to understand what's the worst, what should we let overflow, what shouldn't we let overflow. And then Maurice talked about it, you know, expanding public health target sampling. There's all kinds of things you can look for, biomarker wise, community behavior wise. In wastewater, it really is a gold mine. I think I said that once in an interview. But there's also this idea, you know, of how can we use it to inform resource recovery at our plants. So, like, could we use information about how the wastewater is behaving in our collection system to change our operations at a plant to put more phosphorus into our biosolids, right? So that ultimately is something where we were taking more nitrogen or phosphorus nutrient-wise out of systems and locking it up in something that's more reusable. Really, I think that the sky's the limit when it comes to this stuff. So that was all I had, unless I have more time to go through another use case. I thought we only had until 2, but I guess it looks like we have until 2:30. But I don't know, there's a lot of questions. Maybe we'll just
Scott, you have time
start
if you
asking
want.
questions.
I think we do have until 2:30. We have a couple questions in the Q&A, but if you want to go through 10 minutes more of your other use study, that's fine.
Yeah, so I guess I'll preface it by so can we switch to the next slide here real quick? So the last use case that I told you guys about was drilling up into a collection system, right? This one will be, we know what folks are doing, and like Angel in El Paso, we wanted to present an industrial user with information to try to change their behavior. But first, I'll give you a little bit of history in Cincinnati. If you've never been here before, this is historically a beer town. There were tons and tons of breweries that operated historically, and some that have operated in the same site, discharging into the same pipe for 140 years. Wild amounts of discharge going into really, really old brick sewers. Go ahead and switch slides. This is a specific area of downtown called the Brewery District, and every spot that is in red is an area where a brewery had operated at some point or continues to operate until this day. So if you would switch slides again. We got a lot of old brick sewers around here. Our infrastructure is old, but generally well maintained, except for areas that are downstream of industrial discharges. So this brewery that has been operating, I think this one has been discharging continuously into some sections of this pipe for about 110 years. And they are a nationally known brewery. I'm not going to throw them under the bus here. But you can imagine food and beverage manufacturers, the industrial effluent that they have can be really basic and really acidic at times, depending on what they're brewing. So go ahead and change the next slide. So what we decided is, this is more of establishing a pattern downstream to understand what the impacts of industrial users are downstream. So I use that same photo of Andy in that auto sampler that's there, and we put it just downstream of this industrial user to collect water quality information about what they are discharging into the sewer. So if you could go ahead and go to the next slide really quickly. And what we saw there was really, really interesting, right? We saw these wide swings of corrosive material being put into the sewer, and they brew a lot of different type of stuff there. Not specifically White Claw, but that's the seltzer that everybody knows, so I throw that out there. And there, you've probably heard ain't no laws when you're drinking claws. That's more of the certain, not this neighborhood, but other neighborhoods in Cincinnati, you would see that. But these wide swings in basic conditions and acidic conditions have caused that kind of problem at the bottom of that sewer there that I showed earlier. So we allow folks to put industrial wastes that are between the pH of 5 and 12, that's a federal regulation. It's actually fairly generous. I've heard of other folks that have much more restrictive sewer rules, but that's what we have. And you can see there were a number of excursions on the low end of this. If you could go ahead and switch slides. Once you have that, if you have that over time, it can cause problems to your sewer. That's the bottom of an old brick sewer that's just downstream of that, that the mortar's all eaten out of. And we've since actually repaired that. Go ahead and switch slides. So we decided to start moving that sampler downstream to understand the impact of the industrial customers. A couple of over, I think can't remember exactly, but downstream, maybe a quarter mile, half mile downstream, all the way down to the interceptor. So if you could switch slides, we started moving it and seeing the same pattern downstream. Over time, you saw these wide excursions of water quality that was being put into the sewer. And if you'll move to the next slide, we just kept moving it downstream, right? Move to the next slide. You're seeing the same pattern downstream. You've moved a number of manholes down. I believe you're a quarter to a half a mile downstream at this point. So you're still seeing that impact downstream. Keep going. And then we moved it even further downstream and actually fairly close to our treatment plant at this point, which has a gigantic interceptor that I don't think could really be influenced by an industrial user that was putting this type of material in the sewer. We've never seen wide pH swings at our raw influent, though they are very, very close in distance. But one of the most interesting things about this was if you switch slides again, switch it one more time, same pattern. But the size of the sewer increased dramatically over this study. So you went from a 12-inch to a 24-inch to something I could walk through, to something you could drive a Mack truck through, right? 114-inch sewer, that's massive. And you were still seeing that industrial impact that far downstream. And the receiving streams of that, the sewer sheds, the catchments of that got larger and larger. So you had more and more water that should have been diluting that. But really, it was really just really, really strong stuff. So if you keep going. So what did that information, that real-time in-system water quality information do for us? It allowed us to understand that this brewery was constantly violating for pH due to a lack of pretreatment system. They just didn't have it on site. They weren't neutralizing. They didn't have a holding tank that they were letting it sit in. It was just being directly discharged to the sewer. And we were doing spot checks, just like Angel talked about. And our traditional sampling and enforcement mechanisms, generally, they move pretty slowly. But this real-time in-system pollution data, along with the sewer inspection information that we presented to them, changed the behavior of this user. And we, have this says that we will likely expand to other suspected violators. We've already done that. We've taken it at, we're monitoring some of the other breweries in town, some of the other big dischargers, to try to understand, if they're having impacts downstream. And go ahead and switch slides. Oh, that was it. I thought I had one more, but I think I moved it up to the last one because I didn't think I was going to have that much time. But I want to thank everybody again for having me at NACWA and the folks at Kando to talk about this technology. And let's see, I had 10 minutes. I took 9, so I'll give back a minute.
Thanks so much, Scott and Angel and Ari and Maurice. Thank you all for your really thoughtful presentations and contributions to today's Lunch and Learn. So I want to get to a few of the questions that came into the Q&A. I think a few of these were from earlier presentations. So I think this first one might be for you, Angel. Have you used any field equipment to measure and transmit toxic load, or is it all artificial intelligence? That also might be for Ari.
Yeah, no, we don't have any additional sensors located where the Kando sensors are located. That's an interesting idea, though. It wouldn't be a bad thing to compare to see what type of water quality you're getting using a different instrument or perhaps using a different method. So I think it's a great question. And if you're serious about enhanced source control, it doesn't hurt to have 2 different sources of data coming in.
Excellent. And this is probably a follow-up to your presentation as well, Angel. It's from Sanja. How do you define a pollution event in El Paso?
Yeah, a pollution event is defined by how the Kando software, the algorithm that it uses. Scott mentioned the 4 parameters that the sensor measures. It's pH, temperature, conductivity, and oxidation reduction potential. It's constantly streaming data from the water stream and taking that data based on those 4 analytes and converting that data to what's called a pollution strength. So the extreme pollution strength is the worst case. It may not necessarily be that something is wrong, whether it's high or low with each one of those 4 analytes. It may just mean that, as an example, out of those 4 analytes, maybe your pH dropped from a 7, a 6.5 to 7, all the way to a 1.5 or a 2, and that would equate to an extreme pollution event. Anything like that would have an extreme change in what we would consider the baseline wastewater quality would be considered a pollution event.
Just to add, thank you, Angel. To add a bit behind the scenes in terms of the algorithmic pipeline, we have several stations in the data pipeline. One is an anomaly detection algorithm that has a baseline, much like Andrew just mentioned now, and there is 2 standard deviation from it. That's one sign, and then we have statistical rules that will yield an event. And then in terms of usage, you can decide what is where will you take action. But that's in the pipeline, basically, how we will process the data and say, this is an event.
Great. Thanks, Ari. I want to go back to an earlier question that was submitted in the chat box from Marcus Lee. And I think this was for you, Ari, and Annie Lee answered it, but what can the Kando overview tool predict in influent loading? And I saw Annie Lee said that there's some machine learning happening, and you can predict hydrogen sulfide as well as organic loads. But the one piece that was missing on this was, where do you guys stand on detecting PFAS?
Again, so what we can detect today, I'll go a bit on the technical side. The way we detect with our contactless sensor, we have the fluorescent excitation of material, and then cameras that absorb it, and then there is a signal. This signal is then transferred into a machine learning algorithm that we trained based on COD and pH, EC, etc. So we created a data set during the development of the product, and this is how we read it. We can detect other materials, but for now, this is what we concentrate on, and we have a roadmap for this to develop more machine learning algorithms, more models to detect other materials. PFAS is on our list. It's a part per billion. It's a more challenging one. We're looking for proxies for PFAS. This is a part of our research. We will let everybody know this is a hot topic, we know, and we're working on it as well.
That's great. Thanks, Ari, for that. I think there were a couple other questions that came through. This one's for our folks in Cincy. This is from Carrie Turner, were the water quality sensors affected by the low pH or other corrosive conditions you observed? And did the sampling lead to taking the sewer photo and discovering the dye? That's for you, Scott.
Yeah, so the water quality sensors, anytime you have water quality sensors and they're submerged, you got to deal with rags, you got to deal with wipes, right? So there is some maintenance associated with them, but no, we didn't see a whole lot of issues with corrosivity, even though they were downstream of some pretty nasty stuff. As far as I know, they hold up pretty well. Got to go out and clean them every once in a while, but that's and we don't have it yet. The contactless one, I think we're going to get it this year. I'm pretty excited about that. See how that works compared to something that you got to go out and check on all the time. And then the second question, did the sampling lead to taking the sewer photo and discovering the dye? No, it didn't. Me trying to understand what lateral might have been conveying the really kind of nasty stuff led me to go into our sewer inspection system, which is another data system that nobody in the pretreatment world that sits in my division ever looked at. And so I thought, well, why don't I go and look and see what the sewer looked like there? And the only inspection was from 2009. So that is now, this company's been operating there for a really, really long time. We actually ordered a new inspection to happen of it. So there'll be a new one that happens to that pipe downstream of there to understand if there's more corrosion that happened because of that influent or effluent, should I say. But no, it did not. That was just me being curious and then identifying another data source that helped me solve a problem. So it's not the best picture. I know the video was terrible too. It's really shaky. I think somebody was actually walking through the pipe when they were doing it. They wasn't using these neat robots that they have now and do the inspections, or flying a drone through, like I think some people are doing. Yeah, but I will have something, so maybe I'll come back and I'll show you a nice 1080p video of it at some point, and then some data directly from measuring it from that lateral at some point. Yeah.
That would be great, Scott. Photos always tell the story so well.